So we're going to try to finish this thing today. And where are we? We have, quickly summarize, we are trying, if. So we have the 3-manifold, which is obtained by surgery on link L1, and it's also obtained by surgery on link L2. And then we are trying to show that L1 is equivalent to L2 in these two moves. So we know that L1 is equivalent to a link L1 prime, and L2 is equivalent to a link L2 prime. Back to 1 and 2. Such that the 4-manifold XL0 prime is equal to the 4-manifold XL1 prime. And then we'd like to show now, so we're down, the primes probably shown there, but anyway, I'm not going to drop the primes, and we're just going to assume that we're in this situation where the 4-manifolds are equal to each other. And the first step was doing some moves to get the 4-manifolds to be the same. And so we assume that XL0 equals L1. And remember, each L0 and L1, L0 and L1 give you Morse functions, F0 and F1, from n to 0, 1, x to 0, 1. Morse functions f sub I equals 0, 1, from this, let's just call this I call this. Originally, X was the 4-manifold I got by going XL0 and XL1 at the product. Now forget that. I'm just going to call this new form X. So I get these two functions, f sub I from x to 0, 1. The boundary of x is equal to n. And these two Morse functions are such that f sub 0 gives, they both have only indexed 2 critical points. They both have m at the top. Here's m. Map to 0, 1. Sorry, they have 1 index 0 critical point and lots of index 2 critical points. Okay, so F0, F1 both have 1 index 0 critical point. Some number, actually the same as we discussed, and some index 2 critical points, but no index 1 critical points. And then we choose a generic homotopy. F sub t connecting them from x to 0, 1. Now we can assume that for all t, F sub t has 1 index 0 critical point. That uses argument 4, and now we want to soup that argument up to arrange that for all t, f sub t has no index 1 or 3 critical points. We know we don't, we can also, and no, I didn't say this, and no index 4 critical points. I mean, the general thing we said was if I had a coordinate for something non-empty to non-empty, then I can assume there are no minima or maxima, no index 0 or 4 critical points all the way along. Now I do have the single minimum, but I can reduce that theorem by removing the ball from each of them to the homotopy there. So then I never need to introduce any maxima. So now goal is to eliminate index 1. 3 critical points, and we'll do index 1, and you'll see that the index 3 case is just the same thing upside down. And having achieved this goal, we will be done. So what we want to eliminate then, we're going to change x once again. So this is going to change x. So in this case, we'll change x. I need to also change L0 and L1. So we're going to change x so that by changing L0 and L1, so that then we can do the homotopy without any index 1 or 3 critical points. But once we've done that, we'll be done, because now I have a new x, which has a one parameter family of Morse functions on it with no births. If it has no index 1 or 3s, then it has no births or deaths, because it's index 2 all the way along. With 0s and 2s, births and deaths would have to introduce 1s or 3s. So it's just the same two handles flowing along and crossing and so on. But then the only events that happen in terms of the handle decomposition are handle slides. So at that point, after this, once we do this, once this is done, L0 is equal to L1. So let me focus on how to eliminate index 1 critical points by changing x. So we look at, so you consider the surf graphic. This one parameter family, x and t. And the start looks like this. Draw it in the box. I've got my single index 0 critical point, which I don't really worry about too much. That's if I have it, I got index 0 here, and that just runs all the way across. 0, that's the bottom of the manifold. I've got a bunch of index 2 critical points. Same number, it turns out, on the left and on the right. And so now that the point is in the middle somewhere, I may have the module up. And then we have the birth of a 1-2 pair, so this would be 1 and 2. That's the sort of thing I want to kill. Cross, and another, something like this can happen. It's another 1 and 2. You know, you can imagine some pretty complicated situations. I'm not even thinking about the 3 handles. Now, this particular example sort of might make me think that we could easily get rid of these things, if these are swallowtails or something like we did before, but you can have something come up like that. Maybe this could be pretty complicated, right? And we want to try to think about how you, maybe I should have highlighted the ones in different colors of the problems. Okay. The goal is to try and make those nested, like we did with the zeros in the earlier argument. And so, you could just quickly, all right, let's think now about, I'm not sure how much I'm going to write down to try and explain this argument. That you can look just at the, okay, you can move one of these cusps back, right? This cusp, this birth, for example, you can move all the births to the left as far as you want. But the subtlety now is that there are some choices. Let's just remember what were the issues with moving. Remember, when we were trying to move a 0, like this, for example, if we wanted to say move this cusp down from there, for example, you may or may not be able to do that. And why might you not be able to do that? Well, if you imagine the Morse function that you get by going vertically in this direction, right? You see an index 0 critical point, which means a new component is created. It then later gets attached to the main mass by this cancellation. But at first, anytime you cross an index 0 critical point, that just creates a new, piece of universe all by itself, right? Now this birth is happening at a point, right? And that point could be in this new isolated bit of universe that's been created. In that case, this cannot drop below there, right? And so you have to be very careful. You can, but the trick to do there is you can always move it that way, because that up here, this is a index 1. This is a index 1 critical point. So you can, and it's not whatever this isolated piece of space was that was created, it gets reconnected to something there. And then the other thing is, so you can move these as far left as you want by going on the top. And then you might have ended up with a situation where you have all of your zeros all of your bursts of zeros nicely nested, but you might then have some horrendous sort of twisting happening amongst all of them. And then you might say, well, how do I know that I can clean up that twisting? Let's see, I want to it's lucky, probably. Yeah, it's lucky. It's pure grade in that sense. And how do I know that I can then straighten this twisting out? Well, what could be the obstruction to moving a critical point down? Well, the obstruction to dropping a critical point, remember, is if its descending manifold hits some ascending manifold, runs into another critical point. But here, these are index 0 critical points, so they don't have descending manifolds. I mean, it's sort of obviously, if you have a minimum, you can lower it as far down as you want. Nothing gets in the way, right? You're just moving it through nothingness, right? So in this case, you can take this in the zeros situation. You can take that picture and you can just replace it with a picture where you all go straight across. So what's the difference in trying to do that in the index 1 case, where the bottom now is index 1 and the top is index 2? First of all, there is a certain improvement in the index 1 case, namely that, so now let's compare to the index 1 situation. If I have index 1, 2, and then I have another cusp here, that's index 1 and 2. Now, as you go up in this direction, you're attaching a 1 handle, which means you're not creating any isolated components at any point, right? And this critical point, then, so everything in this picture now, everything's connected. There's no disconnected stuff anywhere, right? And so I can always find this. If this birth is happening at a point, then I can find a path for that point to go, and I can drop it below here. That's not. But the key thing to understand though is that there is actually a choice when you drop it below, and the choice is whether this is a 1 handle. The choice is should that point go down this foot, or down this leg, or down this leg of the 1 handle. So this, when you move this cusp down, there's a choice of which side to go down. And we're going to bear that in mind. That's actually going to be advantageous to us shortly.
But that's just like you just go between them by hand side? Is that?
They're related by hand, right? So a good way to, yeah, I mean, in a sense, what you're doing is you're saying, I've got this is a canceling 1-2 pair, and this is a canceling 1-2 pair. Okay, so there's a 1 handle and a 2 handle that cancels it. Here's another 1 handle and a 2 handle that cancels it. Now, it's sort of, yeah, I mean, the 1 handle and 2 handle cancels could be over here or over here, right? And then as you move from there to there is a handle slide, precisely. And that's actually going to be, so keep handle slides in mind. That's exactly the issue. Because, so using this fact, and you could also go this way if you want to, but actually we're going to want sometimes to go down, right? Using this, you can, maybe the easiest thing to say is you can get, using this you can get, you could pull all the ones down to a certain level, and then you could move them off to the left, and you could easily get to a situation where your ones all, say, are stacked like this somehow. Ones, twos, on the left, and the same thing on the right. And the twos are going to go off somewhere. And now what you could do then is you could get them to a situation where they're sort of something like this, slightly one above the other, and then it's not, yeah, I'm not doing this the most efficient way. If you think about the common torques of it, you can eventually, I'm not saying this right, there's an easy way, this is probably more complicated. There's an easy way once you're able to do this to move all, to nest all the cusps in. So you can get to something where the cusps are nicely nested, but I just want to remember that we had some choices as to how we did it. Right? Because at the time we were moving one handle's below the, we were moving these bursts down across the one handle, and we could have gone one way or the other. But now, what about this possible grading issue? This, and then maybe have some twisting. Oh, another thing to remember is that just leave it just for the moment. Think about. It's not also not obvious that we'll have that these three, that there's a permutation from this set of 3 points to this set of 3 points, and it's not obvious that that's the identity permutation, but let's for the moment assume it is. Okay. So now, what can possibly be the obstruction to untangling this? Again, it's each of these is an index 1 critical point. So as you move up, there's a 1 handle, and in some, that's the simplest sort of situation. Suppose you're in this situation, this is a 1 and a 1, and we want to separate them. What could happen here is that one of these ones rises above, slides over, and then drops down. You could have a handle slide between the given vertical dotted line. And if there's a handle slide between these two, then you cannot drop this, you cannot go to, you cannot clean them up like that. So how do you deal with that? The answer in this situation is that you should have, the answer is that you, say this is your cusp here. The answer is that you went down the wrong side of the one handle. So,
can you try to explain that a little bit more, like maybe?
Why the one handle is obstruction before I do anything else? Okay, yeah, why the handle slide is obstruction. Okay, there's sort of an abstract and a concrete way. Let's try the abstract first. The abstract way is that each of this just is, whatever index these critical points are, okay, they're the same index. They each have the same index, and so they have descending manifolds, each of them, right? And we know that for an isolated, fixed Morse function, generically we expect the descending manifold of 2 critical points of the same index to be disjoint. So the descending manifold for this guy comes down, the descending manifold for that guy comes down, they miss each other. Okay. However, by a dimension count, we discovered that in one parameter families, you can expect that there will be isolated times when these descending manifolds are not disjoint. And that's precisely what happens in a handle slide. This one handle, this is its descending manifold, this is descending manifold. Sure, they're disjoint, but as it moves along, there's a boom, bad time, and then it continues now disjoint again. And this one time, this descending manifold hits the critical point. Okay? That's what this dotted line signifies, is the time at which there is a descending manifold for this intersects the ascending manifold for that. Sorry, I should say, the issue is not descending manifold being disjoint. The issue is descending and ascending being disjoint. Okay? Ascending for this one being disjoint for descending for that. And if the ascending for this one is disjoint from descending for that, remember we can lower the value of a critical point by modifying the Morse function in the neighborhood of the descending manifold. So that you can just drop it as far as you want, as long as you're staying near the descending manifold. But as soon as your descending manifold runs out, it hits into something else, that process no longer works. Okay. So now if you've got this one time when that process doesn't work, then you're stuck.
Okay.
There's also a much more concrete way to think about it is here's when I'm moving along, this guy's below, right? Now this guy goes up, that's the first crossing, so that it can slide over, and then it goes back down. Right? Now, I want to replace that with something where this guy stays down all along. Right? Well, how can I, in the process of going, it had to go up in order to slide to get back down. Now I can't it can't do whatever it did, right? And for example, these 2 feet might be in different components.
Okay.
That's the worst case scenario, right? And there's no way this thing's gonna end up jumping from having a foot here to having a foot in a different component.
Okay, thank you.
Okay. But the answer is sort of that if, so this handle slide, you could think that this handle slide might have appeared because you started out with something like this, right? And then you and you dropped this down, but you dropped it down, you know, you should have dropped it straight down here, but instead, as you were dropping it down, you dropped it down this side of the one handle. And you sort of created this handle slide. Or another way to say it is, if this handle slide is here, you sort of back this beak up until you sort of, you make this happen earlier and earlier until the handle slide's not there, and then you drop it down. And so you, by choosing, so I think the combinatorics is sort of, maybe tediously they didn't prepare well enough, but, you know, you can sort of, the upshot is that by choosing the, which side, one handle, to go down, when moving cusps left. By choosing these carefully, you can eliminate handle slides. So I don't know if that's really convincing. I mean, if there was originally some handle slide way in the back, there was some handle slide here, right? Then in some sense, you have to, you move. I think the best thing is to move everything. Is first bring everything out, right, to this nice nested position, and then sort of you have lots of handle slides all over the place here. Vertical lines mean just wherever some kind of handle slide is, and then you want to carefully sort of go back, or maybe, you know, say you want to eliminate this handle slide, right? You could do it by, again, dropping this, moving this back to where the handle slide isn't there, and then dropping it down. Another way to say it is you drop it down in such a way that you create an extra handle slide that kind of cancels. So if it happens, if you have 2 handle slides and here one goes over and then back, then you can sort of eliminate those 2 handle slides and then pull it down. So you sort of add, one way is you can keep dropping these down to add canceling handle slides, undoing these crossings, and eventually get to the case where they're nested. Except for the fact that you may have, what if there was one more crossing here, and so this eventually went over, that's not the one I want. This one comes, and it doesn't end up on top, then I sort of have a more fundamental problem in terms of getting it to be, everything to be horizontal, because I don't have the right permutation. I have a non-trivial permutation from here to there. But there's a trick for dealing with that, which is that, let's see if I can, so here's a trick. Trick to change crossing like this to crossing like this. And the trick to doing that is to use an hour and a half ago.
Don't you just like switching them? I mean,
so this is what's that?
I mean, can't you just pass this inner one? Can't you?
Yeah. Okay, right.
Because that's what you're doing.
You're right. That's much easier. Yeah. Okay. Right. Of course. You just add it. I mean, yeah. You just.
Yeah. Right.
Sorry. Thanks. That's much easier. I guess there's a move that I like.
But you've done exactly.
Yeah. Right. Well, yes, exactly. There was something else. There was a local move that I wanted to tell you about because I like it. But I actually don't need it, so let me not tell you about it unless there's a way to do it without moving any cusp or anything, but that's another story. I like it because really it's a, so I claim that think of this as a, this is a one parameter local picture in a one parameter family of Morse functions. This is a local picture in a different one parameter family of Morse functions, starting and ending with the same Morse function. And so you can think of going here and then going back that way as a loop of Morse functions, okay? And it's a loop of Morse functions that has 3 crossings in it. And I claim that that's that's an interesting loop, which is a non-trivial loop in Morse functions, and you have to. So if you're interested in thinking about 2-parameter families of Morse functions, it's interesting to think about how to kill that 2-parameter family. What kinds of disks worth of Morse functions that. What one possible way to do that to go from here to there is to pass through the monkey side, which is this non-Morse. 3 ascending and descending directions. But anyway, this is that. I get excited about it more, I'll tell you about that another time. Okay, so you can get to this. You can get I'm not sure if I did the most convincing argument of that, but I think that's sketches the idea. And then all kinds of stuff is happening with the 2 handles, we don't care. And now this is, here we are at t equals 0, here we are at t equals 1. We have our, well, I'm not going to worry about the other critical points. Now I'm ready to change the 4-manifold in the following way. So remember, there's a 4-manifold, it's all the same 4-manifold all the way across at the moment, right? And so what I want to do is I want to, actually, I think the best way to say that is I'm going to focus now on this section of the, let's say this is t equals epsilon, t equals 1 minus epsilon. And so let's think about, so consider f sub t for the t between epsilon and 1 minus epsilon, and then still I've got the same, so now it just, if you look at Rob Kirby's paper, you'll see what he says is, run the cusps off the end. Okay, I'm trying to say that a little more carefully by, we're going to reparameterize things, so I'm going to focus just on this, and there's a sort of we're going to talk about precisely how you go from this handle decomposition here, which has only 2 handles, to this handle decomposition, which has the original 2 handles, plus a whole bunch of canceling 1-2 pairs. And we'll talk about that shortly. But, so I just want to think about, so f sub f, let's think about f sub epsilon. Right? F sub epsilon has, has a bunch of index 1, has the index 0, and 1 index 0, one of these. And then it's a bunch of index 1 and a bunch of index 2 points. And what I want to do is, and f sub epsilon is a, so I want to now change x. So this is all f sub epsilon. Which is x, 1. And I want to think about, let's focus on 1. I want to take each of these index 1 critical points and trade it for an index 2 critical point. I want to trade these at the cost of changing this 4-manifold x in a way that I can describe precisely. So focus on 1, index 1. Let's focus on 1 handle. So I'm going to think about the handle decompositions now. Or maybe I should, this is very, very parallel to what we did with the 5-manifold, right? So maybe I'll try to set it up just like that. So I'm going to think about x. So epsilon, let's suppose the f sub. Let me think about f sub epsilon inverse of maybe epsilon 2 epsilon. Suppose this has, the lowest index 1 group. Okay, so this is now a slice of the 4 manifold. The 4 manifold is here, and then I'm taking some slice right there from epsilon to 2 epsilon. I mean, I'm just this. I could call this delta. It's not going to be related to this epsilon, but it's just a small number. Okay, and so in here is this index 1 group. So this down here that's the 0 handle. Right there, and then in here, there's a 1 handle. And I want to take this slab out and put something else in, right? Serve it out and modify it. And so in order to do that, I want to understand, what's this level set here? That's S3. What's the level set just above it? Okay, so f sub epsilon inverse of epsilon is S3. There's just a 0 handle below that. And what is f sub epsilon inverse of 2 epsilon? Well, that's S3. That's the result of attaching, it's the boundary of the result of taking a 0 handle and attaching a 1 handle to it. Okay? I claim that's S1. Well, we've done that before. That's when you attach you take 2 balls, right? Remember, you're attaching 4-dimensional 1 handle to S3. Here's S3. Here's our 2 feet of the 4-dimensional 1 handle. Then, the complement of this has got lots of S2s, right? S2's going all the way around. And on the outside, and now on the inside, I've got S2 cross I as well. And so that's S1 cross S2. So I want to show that there's another 4-dimensional coordinate system I can get that goes from S3 to S1 cross S2, which doesn't have any 1 handles in it, and we've also done that. That's this. So notice that, remember, 0 surgery on the unknown also gives you S1 cross S2. Maybe we didn't do that as an exercise. So how do you see this? The best way to see this, this is exactly the same thing. So this means you take the key point is that this handle, the handle attaching circle, bounds a disk. Okay, so it bounds a disk, but not only that, it bounds a whole. There's a circle's worth of disks that it bounds, right? So there's this disk in here, but if you start think of that as a soap film, and you start blowing air from behind, it bubbles out, gets bigger and bigger and bigger, passes through infinity, and comes back around. So there's a whole circle's worth of disks, and then the 0 framing means you fill it in precisely the way so that this circle becomes the new meridian when you do surgery. So then each of those disks matches up with a disk inside the torus and becomes a 2-sphere as well, and you've got a circle's worth. So this is S1 cross S2, i.e. You can replace f epsilon inverse of epsilon 2 epsilon with a 2 handle attached along a 0 frame line. And you have, in other words, taking S3 cross I, attaching a 2 handle along a 0 frame unknot, uses the same 3 manifold at the top that you get by taking S3 cross I and attaching a 1 handle. So we do that operation and we change the 4 manifold, and we now have eliminated a single 1 handle. However, so you can do that, and you can do that all the way across in here, because now once you get these things straight and no handle slides between them, then they're just basically sitting there. Those 1 handles are just sitting there all along, and they're not changing. So you can do that. Well, maybe I should say that. So do that. Do this. 1 minus epsilon, and for all the index 1 critical points. And so now I'm going to draw sort of a graphic of what we have, just to tell you, so you get something that looks like this. This is the picture of the moment we have. Here we are. We've got our 0 that we're just happy about. Right? We've got our original 2's that wander around. And then we've got, those are our 2's. And then maybe they interact with this stuff. We've got our nested. These are our 1's now. And then they're going to, I'll need you to draw some what we had first. You know, and again, then these may wander around and grade those. Here. What happens? Okay, something like that happens. These, at the moment, initially, I'll draw blue, initially these are all bad, all the way across. And I've done something a little fishy.
Like, I mean, I don't understand what happens.
Right, I'm going to show you. So here, so now here's the fishy part, right? The fishy part is I cut, boom, right there, and leave a big question mark. This is your legitimate question, right? So at time epsilon and time 1 minus epsilon, I can make some kind of disjoint operation, right? And now in here, all this stuff is good.
By that you mean 3.
But by that I mean there are no index 1 critical points. However, the manifold has changed. I've done something very suspicious, right? I've changed the manifold at this time. It's kind of hard. So what I want to do instead is I want to show, so this is f sub t from some new manifold x prime to 0, 1. And over here I have I have x from 0, 1. And let's get this is a new manifold x prime. And this here I have this manifold x from 0, 1. F sub t of those. And so what I'm going to do now is show, I'm going to say, well, why can I just throw this away? I'm going to forget about this as a surf graphic. I'm just going to say, going from this 4-manifold x to this 4-manifold x with its handle decomposition to this 4-manifold x prime with its handle decomposition here is, uses those moves. Okay, so remember, here I have, over here at this level, I have x sub L0. Here I have x sub L1. And now, at this level here, I have x prime, which is x sub some L0 prime. You know, there's just some new link here. Corresponding to this Morse function, gives you a handle decomposition on this new 4-manifold. Here I have this is the same x prime, but it's described as x sub L1 prime. And now I want to claim, finally, so we now believe that, because there's only handled slides happening here, we'll now believe that L0 prime and L1 prime are equivalent. The final step is to show that L0 is equivalent to L0 prime. The final step is to show how you go from this handle decomposition. In fact, I should have made it even more evident. This is a little bit misleading. I wanted sort of nothing interesting to be happening other than these births in this handle. Okay, so I wanted to pull the births and all the way back before any other events, any crossings, any handle slides, anything. So what I'm going to do, so here I have a handle decomposition for a 4-manifold. Here I have a new handle decomposition for a 4-manifold that involves one handle, so I've gotten out of the world of a single framed link, right? I've got the balls as well. And then I'm going to jump back to the world of framed links, but by changing the manifold. And so something happens where, remember this is a 1 handle, the one handle is attached to two balls, somehow magically that one handle is going to turn into a component of a link, a knot. Okay, and so the way that happens.
So these red horizontal, those are
two, index two. Index two. Remember, we traded the original coordinate from S3 to S1 precedent to have a one handle. And the claim is that instead of that one handle, which we attach on these two, we get a, sorry, this is precisely what happens. These two balls somehow became this unknotted zero. Now, of course, just throwing in a zero in the middle of nowhere is not one of our moves.
I mean, is that zero, is that unknot like the centers of these spheres?
No, it's actually, here's where it is. It's, so we draw a little dotted line between them to indicate that they're minus of those two. That unknot, the best way to think about where that unknot is right there. So it's
exactly not known as
so now, so the claim is that anytime you see this, a little two balls, indicating that you've attached a one handle, you can throw those two balls out if you don't care about changing the four manifold and replace them by a little unknotted zero circle indicating you should attach a two handle there. But the key thing now and just throwing in, and so, but notice for every one of those one handles we threw in, we also got a new two handle. So this makes us, if I just said, okay, throw in a bunch of zeros, you should be very suspicious that throw in a bunch of zero framed unknots to the link L0. That's not one of our moves. We're supposed to throw in plus or minus 1, 0, okay, but zeros are bad. However, remember that each one of these one handles came with a two handle. So that means each one of these zero framed unknots comes with another knot that is interacting with it somehow. So actually, each one of these come in two component pairs, right? So so at a birth, at a 1-2 pair, what do you really see in terms of, now I'm going to draw the handle decomposition right when a 1-2 pair is born. You get this, and then you get some, you see, a birth happens in a small neighborhood or something, right? So you don't expect the canceling, so this is the attaching circle for the two handle, this is the attaching S0 for the one handle, right? You don't expect this two handle to go wander all around the manifold and come back. It should all be small inside the ball and disjoint from everything else.
What's the framing on that?
Well, so first of all, remember that this is a knot going over the one handle. The one handle is sort of creating an S1 cross S2 component, and this thing is going in the S1 direction, and so it's not null homologous. This knot in the 3 sphere, this loop in the S1 cross S2, in the 3 manifold does not bound the surface. So to write an integer next to it is dishonest because I don't have a preferred zero framing to reference. Okay? There are conventions, you'll see papers in which integers are written next to this, and the convention is that what that really means is that you use this dotted line to imagine that it connects up, and then you sort of pretend that it is a knot in S3, and then you write it right. But the other thing to remember though is that you can, there's a framing that goes, let's draw a parallel push-up like that. It could be like that. I claim it could be anything. Because I can now, I've got the one handle coming down, I can, what does it do when it goes over the one handle? Well, I can spin around arbitrarily, but I can just spin the foot of the one handle arbitrarily. So actually, I claim that this framing can be whatever you want. And it doesn't, they're all sort of equivalent. I mean, in other words, if you attack, I'm saying something that's sort of obvious, which is that whatever framing you attach this with, you get diffeomorphic 4 manifolds. Well, that's obvious because the format, I mean, these cancel, so the whole thing doesn't do anything for four manifold anyway. Whatever framing it is, they still cancel. So we are really very almost done because okay, so I want to think, one way to think about this knot then is it goes around, I mean, adding this, this one handle, we saw it change the boundary by turning it into S1 cross S2. So a good way to think about this canceling knot, this sort of dual knot to that one handle is that it is, so this whole thing is in S1 cross S2, then this is just the, this is just S1 cross some point with whatever framing we want to do. Now, if we're going to, now we can try to understand what S1 cross a point looks like in the zero surgery on an unknot picture of S1 cross S2. So if we draw S1 cross S2 as this, then where is S1 cross a point?
Thank you, that guy.
It links that guy exactly. Right? It's going to go, it's right here. It links that guy. Because, remember, where's the S2? The S2 is the disk here, and then a disk inside the surgery, right? And then the S1 direction is around here, so that's precisely S1 cross a point. So it links it, and the framing can be, you can set up the framings whatever you want. So we can actually, you can make framing 0, 1, 2, 25, anything you want. It actually turns out if you make it 10 million, then and you slide this over that 0, 5 million times, it'll get down to 0. So sliding this over that will change it by an even number, and you can always get down to 0 or 1. Your choice. You could have picked 0 to begin with, but you could also say, suppose it was just handed to you for some reason. You can do slides to get it down to 0 or 1. If this is sort of a good exercise, right? So do this slide. Maybe I should just give that as homework. Show that 0k is equivalent to so then you can always reduce it down to
change it
by 2.
Oh, you can't change it by 1. I thought you said you can get it to 0 or 1.
You can, well, whatever you started
with.
Oh,
if it's even,
you get it to 0 body
by
1, right? So therefore, this is 0 or 1. But we know that putting in a pair of 2 zeros or a pair of a 0 and a 1, we know that both of those are doable by moves. So this is doable. Moves. So the point is, we do this funny thing where we turn the one handles into two handles. We change the four manifold, has some moves. We do all these pairs, and then after that, there's still the handle slides. The nicest application of surf theory. And decided
So a little bit confused as to how you go from this picture with the canceling pair to, like, here you just sort of.
So this is a.
Like, how do you know
suppose there's just one of these for one. That's make it easier, right? I mean, I'm really just talking about one of them. So suppose you only had one single.
Sure.
Okay. So now that picture over there, together with a whole other mess of stuff, right? Pictures, whatever. This is a handle decomposition right there. Okay. And this stuff over here, this is the original L0.
So you're really just erasing that 1-2 pair and adding that off.
Exactly. That's all I'm doing.
Okay, right. It's not the same manifold.
It's a completely different manifold. I've changed.
Right.
Yeah,
Okay,
sure.
sure. Sorry.
I'll say a little bit more about this operation. This one.